In this section, we're going to look at the confinement of reinforced concrete. Confinement is going to give us a number of different benefits, so we want to look at the topic more in depth. By the end of this section, I want you to be able to describe the primary effects confinement will have on the concrete stress strain curve, differentiate between the two types of confinement, active and passive, explain how passive confinement will occur in spiral reinforced columns, explain why confinement is important and how it is accounted for in ACI 318 when designing spirally reinforced columns, and finally be able to use Mander et al. Expressions to calculate the confined compressive strength of concrete. Concrete will experience confinement effects when confining reinforcement is provided. Here we have a stress strain curve for unconfined conventional concrete and confined conventional concrete. So there are going to be several primary effects which we'll look at on the following slides. First, we can see that confinement is going to have a large effect on the ultimate strength of our concrete. Here I highlighted the ultimate strength of our unconfined concrete versus the ultimate strength of our confined concrete, and we can see that the confined concrete ultimate strength is substantially higher than the unconfined concrete strength. How much higher will depend on the type and amount of confinement reinforcement provided. Next, we can see that the confined concrete is going to have a higher ultimate strain at its ultimate compressive strength. So I highlight the strain at ultimate strength for our unconfined and our confined concrete here. And you can see that our strain at ultimate for our confined concrete is substantially higher than our strain at ultimate for the unconfined concrete. Generally, we'll call the stress at ultimate F prime CC, the second C being for confinement, and our strain at ultimate will be epsilon CC. The next effect highlighted here is confinement will allow our stress strain curve to have a shallower descending branch. So in our conventional concrete, we can have a pretty steep drop off. For high strength concretes, we can have a brittle failure. But if we have confinement, we can add some ductility and give us some post-ultimate strength, which allows load to redistribute in actual structures. The final factor I wanted to highlight is confinement will increase our ultimate strain. So you can see here it'll increase it substantially. So our confined concrete is no longer really going to be dependent on the compressive strength of the concrete. It becomes more dependent on the yield strength of our confining reinforcement. So here, one of the failure mechanisms for confined concrete is the fracture of our confining reinforcement. So here, the first hoop fracture is what controls the confined compressive strength. There are two main types of confinement, active confinement and passive confinement. In active confinement, we have an actively applied radial confining stress that's applied around our concrete. So here you can see these blue lines that are highlighted, the blue arrows, would be an active confining stress or an actively applied stress. This will greatly increase the strength in the black arrow direction for our concrete. Our passive confinement is when we have our concrete core and we have some kind of steel or reinforcement surrounding the core. What happens is the steel or the concrete core wants to expand. So as the concrete's loaded, it wants to expand axially by a Poisson's ratio. And for active confinement, we'll have a radial applied stress resisting the expansion of the concrete. Or in passive confinement, we'll have the steel shell that's going to resist the expansion. So both of these will provide confinement to our concrete. We see here now the stress versus strain plotted in blue, and the Poisson's ratio versus strain plotted in green. What we can see is that as our stress begins to increase during the early parts of our stress strain curve, our Poisson's ratio for concrete is about 0.17. Note I also highlight the Poisson's ratio for steel being 0.25. So initially, our concrete isn't expanding our steel is expanding at a greater rate than our concrete, so we're not going to have any confinement effects early. As we approach the ultimate strength of our concrete, the Poisson's ratio is going to increase in our concrete, but it remains constant in our steel. So we're going to start seeing passive confinement as our Poisson's ratio in our concrete passes our Poisson's ratio in our steel. And you can see as we approach our ultimate strength, the Poisson's ratio in our concrete really takes off. So we'll have a greater confinement effects as we approach the ultimate strength, which is when we need the confining effects. A steel tube may provide the best passive confinement for our reinforced concrete column, but we don't always have a steel tube. So we're going to look at in the following slides and in this section how we can take into account the confinement effects provided by spiral reinforcement and by just regular rectangular stirrups or ties. We saw before that for our active confinement, our confined compressive strength was equal to our unconfined compressive strength plus 4.1 times our active confining stress. So this was done, it's some old testing on some cylinders, and so it's an experimentally validated expression for active confinement. Next, we're going to look at how we can take into account the confinement effects with typical reinforcement. The effectiveness of our reinforcement, or our circular hoops or spirals to confine concrete, is going to depend on the longitudinal spacing of the hoops or the pitch of the spirals. So this spacing S between the hoops or spirals, the diameter of the hoops or the spirals. So what's the size of this spiral? The yield strength of the hoop or the spiral, and also the area of the concrete that's confined by the hoop or spiral. So the confined core versus the unconfined cover. The spacing of the spiral or the pitch is going to influence our confinement because we're going to have some effectively confined concrete width at the location of the spiral, and we're going to have an arching between spirals. So our effectively confined concrete area or volume is going to be less in between the spirals than at the location of the spirals. Next, we're going to look at a derivation for strength with confinement of our circular column with spiral reinforcement. We're going to use Richard's active confinement expression as a starting point, and then we're going to take a slice from our circular reinforced concrete column and cut that slice in half. What we can see is we'll have a lateral stress that will be applied as our confined concrete wants to expand. And then we'll have some kind of restraining force provided by our spiral reinforcement. We can set our lateral force caused by the confinement of the concrete, or the concrete wanting to expand, equal to the restraining force provided by our spiral ties using equilibrium. Then we can solve for our F lateral and plug this F lateral into our expression from Richard et al. And this will give us an expression relating our confined concrete strength to our unconfined concrete strength and the characteristics of our spiral reinforcement. This expression is the basis for the ACI 318 requirements for spirally reinforced columns. What ACI says, or what they try to do with their reinforcement limit for the spirally reinforced column is they want their confined column strength to be equal to or greater than their unconfined column strength. So they want to make sure that these columns, when the cover spalls off, it has a strength, or the confined core still has some strength to hold up the building above. So we have our confined area of our concrete times the confined strength of our concrete equal to the entire area of our concrete times the compressive strength of our concrete. We can plug in our FC expression from the previous slide to give us this next expression here. And then we're going to define our volumetric ratio as the volume of our confining steel over the volume of our confined concrete. We can then further rearrange these expressions and make a further simplification as shown here to give us the ACI expression for the required volumetric reinforcement ratio for our spiral reinforcement and circular columns. So you can see that this reinforcement limit is to ensure that our confined column has a strength that's greater than or equal to our circular column strength, not taking into account confinement effects. Before moving on, I wanted to highlight some initial takeaways. The first is confinement will happen if reinforcement is provided. So whether we take into account confinement or we don't in our analysis or design, it's going to happen in our actual column. The second point, when confinement initiates, the cover is going to fall off. So our cover needs to fall off before our concrete core will start to see confinement effects. The third point, you need to ensure that the confined section is stronger than the original section, or there will be a brittle failure when you lose your concrete cover. And the ACI 318 expression that we looked at on the previous slide provides this check. Now we're going to walk through the Mander et al. Expressions that take into account confinement and allow us to find a stress-strain curve for confined concrete. The first thing that I wanted to remind us of is that spalling occurs between spirals. So we're going to have some kind of effectively confined concrete width at the location of our spirals, but that effective confined concrete width is going to decrease between our spirals. You can also see highlighted here our reinforced concrete column with the unconfined cover concrete, and this concrete will spall off when our confinement starts. So then we'll just be left with our effectively confined core contained within our spirals. Here's some figures from the Mander et al. Expressions. You can see that the assumption is that all the cover concrete is lost when the spalling occurs. So we'll lose all of our cover concrete and then only have our effectively confined core. You can also see that part of the confined core between the stirrups also spalls off. So there's some kind of ineffective confined core area between the spirals. Highlighted here is also the definition of S, which is our center to center spacing, and S prime, which is the distance from inside to inside of our spiral reinforcement. We can then use these figures to define an effective area. This effective area is the area of the effectively confined core, taking into account the arching effect that happens between our spiral reinforcement. We can then use this effective area to define a KE factor that relates our total confined area to our effective area, and then use this factor in with the expression that we derived before to relate our confined concrete strength to our unconfined concrete strength. Confinement can also be provided using rectangular ties, as shown on the right. In both cases, we have some kind of reinforcement surrounding some kind of concrete core. In our spiral reinforced case, as we load our column in compression, our concrete's going to want to expand, and our spiral reinforcement is going to be able to directly resist this expansion. In the case of our rectangular ties, as our core concrete wants to expand, our ties are going to need to slightly deform to be able to resist this expansion. So this means that our rectangular ties aren't going to be as effective in confining our core concrete. Mander has a similar expression for rectangular ties as they do for circular ties. You can see that this expression also takes into account arching, but arching won't just happen between our rectangular ties vertically in the column, but it will also happen within the section. So you can see we'll have an ineffective area that happens between ties now within our cross section. So this is the effective area, and we can then use this effective area to find our FR1 and FR2, so our principal direction and other direction restraining stresses, and then use these to relate our confined concrete strength to our unconfined concrete strength. And we'll do this in an example problem later. Next, we're going to take a quantitative look at how confinement will affect our strain. First, we'll look at how confinement affects the strain and ultimate strength. We can see here stress-strain curves for our unconfined and our confined concrete, where in our unconfined concrete, epsilon naught is the strain at our ultimate strength, F prime C. You can see in our confined concrete curve, our epsilon CC is the strain at our ultimate strength of our confined concrete, F prime CC. We'll use the Mander et al. Expression shown here to relate our strain at peak stress of our unconfined concrete to the strain at peak stress for our confined concrete. The other thing to highlight here is that we'll have a certain range initially where our concrete is unaffected by confinement. So in this range, our stress-strain curves will be very similar to each other. Next, we're going to look at how confinement affects our maximum strain of our confined concrete. So we saw before that our confinement will increase our maximum strain. It'll increase our ductility. And the failure of our confined concrete is going to occur when either our strain drops below some critical value, which would signify failure of the concrete, or when our longitudinal steel buckles, which would cause global failure of the column, or when we have a hoop fracture, which would make the reinforcement no longer effective at confining the core concrete. Higher confinement levels will lead to higher maximum strains, and also higher moment gradients are going to lead to higher maximum strains. Our moment gradient is the distance between our minimum and our maximum moments. And decreasing this z will increase our moment gradient. And increasing the moment gradient will lead to higher maximum strains. Here are three different expressions that we can use to find the maximum strain in our confined concrete. One is the Qui and Moley expression from their work in 1991. We have a PCA expression and a Corley and Maddock expression from the 60s. In this class, we're going to use the Qui and Moley expression, which takes into account the volumetric ratio or reinforcement ratio, or the ratio of our volume of our hoops to the volume of our confined concrete. Shown here are stress-strain curves for our confined concrete. This one specifically is from Mander, Park, and Priestley. You can see that we would first find our confined concrete strength and our strain at ultimate strength in our confined concrete, and then we would use these expressions to relate strain to stress for our unconfined and for our confined concrete. We'll do this in a later example. High-strength concrete is becoming more available and more economical for use, so it's being used more. So I wanted to make a couple points about how confinement affects high-strength concrete. The first is high-strength concrete is more brittle than regular strength concrete if it's not confined. So we need to make sure that we're confining our high-strength concrete in seismic regions and areas where we're worried about our inelastic behavior. Second, high-strength concrete requires higher confining pressures than normal strength concrete to achieve similar ductilities. Our higher strength concrete needs a higher grade reinforcement or more reinforcement to properly confine it. Finally, our high-strength steel can confine high-strength concrete adequately. Right now, ACI is debating the use of higher grade steels to be used as transverse reinforcement. The downside to this is we lose a little steel ductility, but the upside is that we can use a similar area of our confining steel to confine a higher strength of concrete. The final point is that our confinement isn't going to have as much a benefit on the high strength concrete in terms of strength and ductility gain. You can now go to the separate video to look at this example problem, where we're going to find the stress-strain relationship for confined concrete within the below section, using the Mander et al. Expressions. Shown here is a list of additional references for further study on the confinement of concrete.